In this video, we'll focus on Theorem 3.8 from section 3.2 of the text, and it states that every field is an integral domain. So we've talked about integral domains, we've talked about fields, but we've yet not made it clear that every field is an integral domain. And we can also ask the question, is every integral domain a field? So let's focus on this theorem first before we consider the question I just posed. To prove this, we'll start by just letting F be a field. We want to show it's an integral domain, so we're going to assume that we have the product of two elements in the field A and B equaling 0. We want to eventually show that either A is equal to 0 or B is equal to 0. So if A is equal to 0 off the bat, then there's nothing to prove. So let's assume it's not equal to 0. Well, since F is a field, this means that A is a unit. And that's because every non-zero element in a field is a unit. That means there exists an A inverse such that A times A inverse equals 1. So we have the following. If we consider our element B, that is equal to B times the identity. We haven't changed anything there, but we've just stated that we can rewrite 1 as A times A inverse. So we'll replace this 1 here with A times A inverse. Now if we look here, this B times A, that's going to be equivalent to 0. And the reason that I know that B times A is equivalent to A times B, so I'll write that first, is because every field is a commutative ring. So I know that B times A is equal to A times B. And what is A times B? That's 0. So I get 0 times A inverse, and that's just equal to 0. So this tells me that if A is not equal to 0, then B is equal to 0. In either case, A is equal to 0 or B is equal to 0, so F is an integral domain. A follow-up exercise to this theorem is to consider the following question. Is every integral domain a field? So namely, does the converse to this theorem hold? And so if you think about it, no, we've seen plenty of integral domains that do not have, where every element does not have an inverse. So for example, the integers in particular are an integral domain. But it's not a field, and it's enough to just state one element that doesn't have an inverse. So for example, 3 does not have an inverse. In fact, the only elements with inverses are 1 and -1.